Assalamu alaikum dear students. Today we have week number 13 and lecture number 1. This lecture number 1 is continuing with the previous week lectures, context free grammar. In this lecture we will see some more advanced examples on context free grammar, and at the end we will also see how we can implement context free grammar using tree concept. Okay, so let's continue with the examples. The example is that we have the input set of A and B. We have certain production rule. So keep in mind, whenever we see a capital letter on the left side or on the right side, that is called non-terminal. Okay, and the small letter, that is the terminal. Terminal is the actual output or transition we'll use. Okay, and the non-terminal, this is like state. Okay, so I will not repeat it again and again whether it's a terminal or non-terminal. Okay, so we have certain production rule or condition given for the following input values, that is A and B. So that is the S is equal to AB, S is equal to BA, A is equal to small a, capital A is equal to A small it is. Then we have A is equal to small b a, then we have b small b, b is equal to bs, and b is equal to small a bb. So that is some rule which is defined based on the input and the required output. Okay, this grammar generate the language equal the language of string with number of a's equals to number of b's. Okay, it is to be noted that if the same non-terminal have more than one production, so we can write in a single line. Okay, like for example we have in the previous slide we have ss, we have aa, and we have bb. So for repetition of rules in a individual line, so we can combine all of them in a single line using by concatenation symbol. Okay, so let's see another slide. That is, for example, we have S is equal to AS is equal to BS, and S is equal to empty. So we can write using by symbol concatenation. So S is equal to AS concatenation BS concatenation empty, or sometimes it's called OR. Okay. It may also be noted that the production S is equal to SS or empty. I will define the language which is very close with respect to the concatenation. Okay, the language expressed by regular expression of type R steric. Okay, such type we can also represent that is the steric language. Okay, it may also be noted the production S is equal to S is defined the language expressed by R plus. Okay, so we know already the definition of steric and plus as well. So in this slide we have learned if we have a repetition of non-terminal on the left side, so we can concatenate it using by concatenation symbol. Okay, we have example over here for context free grammar with the input values A and B. So we have such production rules, that is 1 2 3 in 1. We have the non-terminal S is equal to, so we can also represent that is equal to with question symbol as well. Okay, that's optional. So in one we have non-terminal S is equal to three terminal, that is y x y. So further we have the definition y and x, and rule 2 we have the definition y is a non-terminal is equal to a terminal y non-terminal concatenation by b non-terminal y non-terminal concatenation empty. So writing in 3 lines for y, so we can combine in one. Okay, so it's very easy for optimization purposes, which reduce the computation, communication, and storage costs as well. So third rule we have, that is the x is equal to 3 times terminal B values. Okay, it is observed that using the production line 2, y generates empty, right? Y generates A and y generates B as well. Y also generates all the combination of the of A and by and B. Okay, thus Y generates the string generated by A plus B whole stack. Sorry, it may also be observed that the above context-free grammar generates the language expressed by A plus B whole stack 3 times B A plus B whole stack. Okay, if we can see from this rule, based on this, so we can say we can generate this regular expression. So based on this production rule, we may generate 4 other words. Okay, so let's see how we can actually here we have the benefit. The x is constant here, right, and y at the end, and starting it has three values, so we may change accordingly. Okay, so let's see in the next slide how we can generate 4 patterns. Like here, s is equal to y x y. We already know this x is constant, so we just place 3 times b, and this y we replace with the empty, right, and this replace with ay, if you know from here. Okay, then we have replaced the 3 times over here. Okay, we have put it this one. Okay, we have a b y, so we have obtained this by from this y. Okay, we replace this y with by because we have the rule over there. After that, we want to omit this y, so we know y is also equal to empty. So this is one pattern, like a b b b b b. The user may also ask like he has a pattern a b b b b 4 times b. This is one of the type. Second, we have another possibilities, right? Okay, this y replaced with empty, right, and x with 3 times b already we know, and this y replaced with ay. Okay, so then we have this one we omitted, then we have 3 times b, the same. Okay, we have a, and this y replaced with by. Okay, then we have replace 3 times b a. Okay, and this again b, and this y replaced with ay. Okay, and finally we omit this y with empty, and we got finally 3 times b a b a. Okay, same for here. Okay, we have y x and y. Okay, so that is replace y with by. This is constant x value 3 times b, and also represented with ay. Okay, so this time we use different values instead of empty for y. Okay, so next we have b, and this y replaced with empty, the same. Okay, and a, and this y replaced with by. Okay, then we have method this one, so we have 4 times b a. Okay, and then we have a b, and this y replaced with by. Okay, so we got this pattern, and finally we omit this y with empty. So the final version, that is the 4 times b a, 2 times b, and a. Okay, another last sequence we have, this is constant 3 times b, this is represented with by, are replaced with by, and this is replaced with ay. Okay, so we easily just omit y by empty. So finally we get 3 times a, sorry, b, and b again, and a. This is the pattern. So we may generate according to our requirement. This is one of the good example, right? Why we have 4 or maybe 6 or 10 times different outputs. That is depend on the required output. Okay, so that's why we can change accordingly. We have another example. Let the terminal be a and b. Okay, there is the input value in the non-terminal, which is the state, that is the x y, s x and y, Production rules are given, that is s is equal to xy, x is equal to ax, x is equal to bx, x is equal to a, y is equal to ya, y is equal to yb, and y is equal to a. Okay, we can see that any string of terminal that comes from x must end in a. Okay, that is one of the thing which is another observation. In any word ending in a can be derived from x. Okay, this is the second observation. For example, to derive the word b a b b a from x, we can easily process with following production rule, that is bx. Okay, so bx, then we got bax, then we got bx, and then we got bbx, and finally x with a. So okay, so keep in mind this thing. Actually, we have required this thing to obtain from this condition. So this values from this we have to tag accordingly. Okay, so if previously we have this thing, we have done with 4 pattern. Okay, so same the case is over here. Okay, we have another example for the y. The word that can be derived from y, and exactly those that begin with a. To derive ab, for example, we can proceed y is equal to yb, yab is equal to ybab, and ybbab, and finally we replace y with a over here, and we get abb and ab. Okay, so we have obtain the particular output from certain condition. So we have to be very clear, and we have to be very focused in choosing to get the required result. Okay, also with continuation with the previous slide, AY always stays on the left side and until it is replaced by an A. When an X part is concatenated with Y part, a double A is formed. Okay, this is one of the things. We can conclude that starting from S can derive only words with a double A in them, and all of these words can be derived. For example, to derive B A B A A B B, we know that X part must end with the first of A of the double of A's. Okay, and then Y part must begin with the second A's. Okay, so we have to obtain such thing. We know xy, then we replace xy, getting the b value as well. Okay, then we replace baxy from that particular production tool, that we obtain bab, instead we have xy. So accordingly, this condition and this required output, so we replace accordingly. So finally we get that ba a and bb. Okay, just by replacing the original non-terminal with the terminal values. This is the mechanism how we can get required output. We have another example. Okay, the production rules, that is S is equal to SS concatenation XA and concatenation empty. X is equal to BX and A. Okay, so based on this thing we can get A static, AB static, AB static, and the whole static. Why we put the whole static? Because for both condition we have empty and empty. First point. Okay, second point, we always start with B, because x over here, x is here also in condition 2, and x also in condition A, right? So this x equal to B with the x or empty. Okay, that's why if I say x is equal to bx, okay, so B, it's placed over here, and then x is equal to A, this A. Okay, so we have a again, right? So we have to complete this series. That's why we have repeated this b and a in b, right? So that's why we put it the b stirring for this, for here as well, in the whole this production rule as well, with the stirring due to empty. So that's why. Okay, so this is the solution. Next we have input value, this is A and B. The production rule, that is A is A, concatenation B is B, concatenation A, concatenation B, concatenation empty. The above context-free grammar generated the language palindrome. It may be noted that context-free grammar. Okay, so such pattern present the palindrome. So over here, that is x is equal to A is A, concatenation B is B, concatenation A, concatenation B. Okay, so if we see in these two production, so here we have extra empty and here we do not have empty. So this is the palindrome representation, and because of we don't have the empty, so this is non palindrome, so context free grammar. Okay, so because of only one empty set, so it gave a big differences. Okay, we have input is A and B, production is S is equal to A is B, concatenation AB slash empty. Okay, so if we see such pattern, so we may understand that is equal to A the power n and B the power n, and the values of n, that is equal to 0, 1, 2, 3 up to many values. Okay, so that is the representation, or we can design such production rule for this. We have another example, context-free grammar for the same input A and B. Okay, so that is equal to S. First one production rule, that is S is equal to AXB, concatenation BXI. Second, we have X is equal to AX, concatenation BX, and concatenation MP. Okay, so that it means we have the beginning and ending with different letter, because we have empty over here, we do not have empty over here, and the other thing is here we have different condition, different output for condition 2 and for condition 1 as well. Okay, so here the assignment goes, that is the construct the context-free grammar for the language of string defined from A and B. Okay, so the condition is basically that is the beginning and ending and same or with the same letter. That is important. Okay, we have very small topic on the trees, implementation of context-free grammar. Okay, so whenever we implement the tree, so for that we need the parse tree. So what is the parse tree? The parse tree actually tell us to determine how to construct a valid sentence under the given grammar condition. That is called the parse tree. Okay, so let's see, read from the slide. As in English language, any sentence can be expressed by a parse tree. Okay, like for example, compiler construction, or designing the compiler to see whether the syntax of if statement or loop or any other keyword according to the definition or dictionary definition or not. So that is done with the support of tree. Okay, tree we can also use for different decision making purpose like hashing. Okay, and cloud security, so we use the tree as well. It's very well known technique, the tree one. Okay, so the parse tree technique, so any word generated by the given context free grammar can also be expressed by the parse tree. Like we have an example, s is equal to double a is equal to 3 times a concatenation b a b and a. Okay, so that is the explanation how we can uh, generate the parse tree, but we will show with the tree example. Okay, so here we have b a b can be generated by the above context free grammar. From this we can generate b a b b b a b. Okay, we can generate to express the word b a b as a parse tree. Start with s, replace s by starting a of non-terminal, going down the line from s to each character of the string as follows. So we have to show how we can get a b b e from such production rules. So first of all we will draw s, then we have to child, that is AA. The further child, we have three types of production rule. So three types of production we have to keep in mind. We have to achieve BAAB. So for that we have to say this one. Okay, then we have AA. Okay, and then we have B. So we can construct by doing. Let's see in the coming slides. So we have the parent node, that is S, and child node we have A and the left and right. Okay, then okay, now let the left A can be replaced by BA and the right one replaced by AB. Okay, so like this one A. Okay, we this is the same. Let's come over here. Okay, we record B AAB and small. Okay, so this A, if we see BA BA, okay, because we start with the BA. If it is start with AB, so we can use this one. Okay, so we have to use A as well. Okay, so here BA, and next we have to achieve that is the B ending. Okay, so we use this one and this one. This is on the left side, and this is on the right side. Okay, because we have start and end with the same. Start and end with the same. Okay, that's why we the right one we replace with AB. Move next. Okay, so replacing we need to replace only the two child, that is A. These two A replace with small a. Okay, according to this one. Okay, this one A is equal to A, small a. So that is how we can use the tree to generate or express the given expression values. Okay, using the context radio. This is another mechanism. Hopefully you have understand how it works. Okay, thus the word ABB is generated. They are both trees to generate. The word BBA is called a syntax tree or generation tree or the derivation tree as well. Okay, so such activities which we have done on the tree, parsing tree, it is known by three names, that is syntax tree, generation tree, and the derivation tree as well. So hopefully you understand this lecture. Thank you so much.